Okay, we are entering into related rates, which is a huge, huge reason why calculus was ever even founded in the first place. Was we wanted to kind of come up with how objects' rates related to each other. So, some quick reviews. What you will learn about is related rate equations, the solution strategy to help you solve these related rate equations, and then simulating related motion. Related rate problems are at the heart of Newtonian mechanics. It was essentially to solve such problems that calculus was even invented in the first place. So let's kind of just discuss what we're even talking about. So I have an applet here to show you. We have this snowball here. We can see that the snowball is in the shape of a sphere, and we can see that we have a radius of our snowball, and the radius of our sphere is 70 minus 2t. Okay, that is the radius value of my sphere. We can also see then that if I put my radius value in for my volume formula, the volume of a sphere is 4/3 pi r to the third. 4/3 pi r cubed is the volume of a sphere. Okay? Now, what we have over here are two functions, two graphs of functions. We have our volume function, okay? And we can see that as this snowball melts, the volume is going to decrease, okay? And then down below, we have the rate function, or the derivative function, which we can see that the rate at which the radius is decreasing is really going to increase the volume of our, decrease the volume of our snowball. Now, I'm going to just play this applet, and you can see that over time, as this snowball is getting smaller and smaller and smaller because it's melting, we have time 8.4, so we're going to say that's 8.4 seconds. So 8.4 seconds later, the volume of our snowball is 630,000. The radius is 53.2 units. The rate that our volume is decreasing is negative 71,000, and the rate at which our radius is decreasing is negative 2. Now, that should make sense. The rate that our radius is decreasing would be the derivative of our radius function, which would be just negative 2. And you can see that over time, that radius function here never changes because it's a constant decrease, a constant rate of decrease. But as that is constant, that really affects the decrease of our volume, because over time, as the radius gets smaller and smaller and smaller, but yet that it's staying at the same rate, that it's decreasing at the same rate, it's changing the volume. It's increasing the volume's rate of decrease. So I'm just going to keep playing this, and we should see over time. Let's play this one more time. Right now we're at time 0, so V of 0 is 1,436,000. That's our volume, our starting volume. Our starting radius is 70. Okay? As I play this, and let's just pause it one more time. After 18 seconds, here is the volume of my snowball. Here's the radius of my snowball. Okay? Here is the rate at which my volume is decreasing. That would be the derivative of the volume. And this is the rate at which my radius is decreasing. That's staying constant because my radius is a linear function. And the snowball is gone. And it's back. Okay. So, we are talking just basically about how the volume rate is affected by the radius rate. That's what related rates mean. So we're just kind of coming up with these equations, then finding the derivative of them all with respect to time, because that's what a rate is. And then we're going to see just how they are related by putting values in and seeing how they compare. Okay? So, that is the applet we're going to talk. The steps for related rates problems. The first thing you want to do is kind of draw a picture. A picture really helps quite a bit, or a sketch of some sort that you can see visually what's happening. A lot of these are geometric situations that we're talking about. The second thing we want to do is write down the information that we know. For example, if we know that the radius of the snowball was 70 minus 2t, that's something we want to keep in mind. Number 3, write down what we're looking for. What is it that we're trying to find? Are we trying to find a rate? Are we trying to find an, maybe not a rate, but an actual value at a certain rate or whatever? So figure it out what it is that you're looking for. Number 4, write an equation or find a relationship between the variables. For example, if I have a right triangle, the relationship between the variables is a squared plus b squared equals c squared. You're writing the equation, or you're at least just trying to come up with some sort of relationship between the variables in question. And then step 5, we're then going to differentiate both sides with respect to t. That should make sense because we're talking about rates, and we've said that the rate is the derivative. So we're going to be differentiating this whole time. And then we're going to evaluate our answer, step 6, by putting in all those values that we found from above. Okay, those are your steps for solving related rates problems. Now, the best way to go through and teach this to you is just to go through some different examples. So I've got a PowerPoint here with about 3 or 4 different examples in it, and we're going to go over each of them. Now, I have a review problem here which involves the differentials that we've been talking about in 4-5. Consider the sphere, a sphere that has a radius of 10 centimeters. If the radius changes 1.1 centimeters, a very small amount, how much does that then change the volume? So remember, we would go through and we found, okay, here's the relationship between volume and radius. Volume equals 4/3 pi r cubed. So then to find the differential, to estimate that change, we found the derivative. So the derivative would be dv dr would equal 4 pi r squared, right? I'm taking my 3 off the back and I'm multiplying it to the front, which would give me a 4 pi r squared. Then remember, we multiplied our dr to the other side, so we have the differential dv equaling 4 pi r squared dr. Then what I can do is I can put 10 centimeters in for r and 0.1 centimeters in for dr, because that's the change, right? And when I solve that, I get dv to be 40 centimeters cubed, or 40 pi centimeters cubed. So what we have found is that if I change the radius from 10 to 10.1 centimeters, then our volume is going to change by 40 pi centimeters cubed. Okay, so that's from 4-5. Now suppose that we have a radius that is changing at an instantaneous rate of 0.1 centimeters per second. So imagine kind of like the snowball, but it's increasing actually because we have a positive 0.1 centimeters per second. So my radius is changing, my sphere is getting bigger by 0.1 centimeters per second. The radius is getting bigger by 0.1 centimeters per second. So you want to think about the soap bubble or a balloon getting bigger over a period of time. Okay? Again, I have a relationship between my volume and my radius. It's 4/3 pi r cubed is the volume of a sphere. What I'm going to do now is find the derivative. See, if I have a relationship between my variables, then I have a relationship between my rates. So what I'm going to do is find the derivative of 4/3 pi r cubed with respect to time, because that's what a rate is. It's an amount divided by the time it takes to get there. So the volume would be, the derivative of volume would be 1, and then you've got to chain on dv dt equals, now we're going to take the derivative of 4/3 pi r cubed, so I'm going to take my 3, multiply it onto the front, and so I would have 4 pi r squared, but I have to take the derivative of r with respect to t, so that's why I have to chain on a dr dt. Now, what we have here, dV dt represents the rate that the volume is changing. dr dt represents the rate that the radius is changing. Now, since I have a relationship between their rates, I can put in the variables or the constants that they gave me up above. From the previous slide, we knew that the radius of the sphere was 10 centimeters, and we also know that the radius was changing at point 1. Well, that's going to be dr dt. I put that in, and when I work out my problem, I can solve this for dV dt and know that the rate then that the volume will be changing will be 40 pi. That is how fast the volume is changing over time if my radius is changing at 0.1 centimeters per second over time. Note that this is an exact answer. It's not an approximation like what we did with differentials. Okay? The sphere is growing at a rate of 40 pi cubic centimeters per second. So that's kind of the gist. You want to figure out what you're finding, come up with a relationship between your variables, and then from there find the derivative. Because if I can find a relationship between my variables, then I can find a relationship between my rates. So here's another example. Water is draining from a cylindrical tank at 3 liters per second. How fast is the surface dropping? Now, imagine that this tank is filled with water, okay? When it's asking how fast is the surface dropping, it's asking how fast is this height decreasing, okay? So, we have a relationship, or we have to find a relationship between the height of this tank and then also the volume of the tank, because that's what the liters per second, 3 liters per second is talking about. It's the volume changing. So, dV dt is -3 liters per second. They told us that up above. It's draining, so it's going to be a negative rate, and it's draining out of there -3 liters per second. You have to remember, and this might be a biggie that you want to make sure you know, 1 liter is the same as 1,000 cubic centimeters. So if it's draining out at -3 liters per second, then that is the same as -3,000 cubic centimeters per second. So that is dV dt. We are looking for dH dt, right? How fast, the rate, how fast is the surface area dropping, or not the area, the surface dropping, or the height. So we need a formula to relate V and H. Well, I have a cylinder, and I know the volume of a cylinder is pi r squared h. Now I know I have an r in there, but what we need to remember is that r is constant, because as my water is dripping out of this tank, the radius is never changing because it's a cylinder. Now if it was a cone, then we would see the radius getting smaller and smaller, but it's just a cylinder. So if I have a relationship between my variables, then I have a relationship between my rates. So I just find the derivative. The derivative of V is 1, and I got to chain on a dV dt, the derivative of volume with respect to time. That's going to be equal to pi r squared h's derivative, which is just going to be pi r squared. Remember, r squared is just a constant. So that would be pi r squared. Then I've got to chain on my dH dt. Now I can put in my values that the problem gave me at the beginning. We know that dV dt is -3,000. So I put -3,000 in for that. That's the rate that the volume is changing. That's going to be equal to pi r squared dH dt. And then I'm just going to solve it for dH dt. So my final answer, dH dt, would be -3,000 over pi r squared. If I would tell you what r is now, you can tell me what the rate is that that height is changing, no matter what r is. Since I haven't told you what r is, we just leave it in this form. Next example, we have a hot air balloon. Okay? Now this hot air balloon, we're not going to take into account any kind of wind, so this balloon is just rising straight up from the ground. Okay? we have theta being pi over 4. That's the angle of elevation of the balloon. So if I'm standing on the ground over here and I'm looking up, this angle right here is pi over 4. I also am being told that d theta dt, which is the rate that the angle is changing, is going to be 0.14 radians per minute. So as this balloon rises, the angle that the rate at which this angle is changing is 0.14 radians per minute. It's getting bigger, obviously, because the balloon is rising. The question is asking, how fast is the balloon rising? So what is it that we are trying to find? How fast, so we know it's a rate, and the rising is referred to by h, so we are trying to find dh dt. Do we have a relationship between h and theta? Well, I do know that the tangent of theta is opposite over adjacent, so that would be h over 500. So now I have a relationship between theta and h. Since I have a relationship between the variables, then I have a relationship between the rates, right? I can get that by derivatizing. We talked about that a couple years ago and we said derivatize. Sorry. We are going to find that by differentiating. So if I differentiate tangent of theta, then that derivative of tangent is secant squared of theta, but you remember you've got to chain on a d theta dt because theta is changing over time, and that would be equal then to the derivative of h over 500. Now, if you want to think about that differently, that's the same as 1/500th times h, so the derivative of that would just be 1/500th, chaining on a dh dt. Now, since I have the relationship between the rates, I can just put in the information that I have. So theta is pi over 4. So I put that in. D theta dt, they told me, was 0.14. And I now have enough information to solve this for dh dt. We have a triangle over here that is a 1, 1, square root of 2. I need that so that I can find the secant of pi over 4. So this angle out here would be pi over 4, which is the same as 45 degrees, and that is a relationship of 1, 1, square root of 2. Secant of pi over 4 is the square root of 2 then, because it's the adjacent, the hypotenuse over the adjacent side. You could also think back to your unit circle, and you know that at pi over 4 we have a terminal point of square root of 2 over 2, square root of 2 over 2. So the secant would be 1 over the x value. So now I have square root of 2 squared times 0.14, and then I multiplied my 500 to the other side to solve it for dh dt. And I see that I have 140 feet per minute. That is how fast the balloon is rising. Pretty cool, right? I like related rates. They're probably one of my favorite things to be doing. Yes, I'm okay with being a weirdo. Truck problem. This is the last example we're going to talk about. U-Haul trucks. Truck A travels east at 40 miles per hour. Truck B travels north at 30 miles per hour. Question is, how fast is the distance between the trucks changing 6 minutes later? So they're taking off from the same place. Truck A is going to the east at 40 miles an hour. Truck B is going to the north, but he's a little slower. He's going 30 miles an hour. How fast is the distance between the trucks changing 6 minutes later? So, some information we need to know. Distance equals rate times time. That's a big one. Distance equals rate times time. So we have truck A. Okay. Truck A's rate is 40 miles an hour. Over those 6 minutes, are we okay with the fact that that would be 1/10 of an hour? 6 over 60 is 1/10 of an hour. So he has traveled 4 miles in that 6 minutes. That's our distance. So we have truck A over here. This distance is 4 miles. Truck B, he's going 30 miles an hour. That's his rate. Over that 1/10 of an hour, he has went 3 miles. So there's truck B 3 miles later. We want to figure out how fast they are getting farther and farther apart from each other. So I can at least figure out how far apart they are at 6 minutes, right? That's just the Pythagorean theorems. 3 squared plus 4 squared equals z squared. So moving through that problem, I get z to be 5. So now we can see we have a right triangle, a 3, 4, 5 right triangle. But what is it that we're trying to find? We're trying to find how fast the distance between the trucks is changing. We're not trying to find the distance between the trucks. We know the distance is 5 between the trucks, but we're trying to find how fast. So that would be the rate. Well, I have a relationship between the trucks, right? X squared plus y squared equals z squared. Well, since I have a relationship between their variables, do I have a relationship between their rates? Yes, we just find the derivative. So the derivative of x squared is 2x, but we've got to chain on a dx dt. That's the rate that x is changing. We have the derivative of y squared being 2y times dy dt, and then that would all be equal to the derivative of z squared, which is 2z dz dt. Just notice that you're always chaining on a d something dt with it whenever you have an object that's changing over time. My 2's all can cancel, right? I can divide them all off. So now I have x dx dt plus y dy dt equals z dz dt. So now we're just going to throw in the values that we can find. We know that dx dt is 40. We know that dy dt is 30. So knowing what we know, let's put everything in. X is 4, right? Dx dt is 40 plus y is 3, dy dt is 30, and z is 5. So now I can solve this for dz dt. dz dt is 50. So the the rate that the distance between the trucks is changing is 50 miles per hour. And there we have it, folks.